Well, good morning, physics kids. Miss Johansson with today's lesson on springs. Springs. Why are we talking about springs? What's so special about springs? Why don't we talk about rubber bands? Well, you know about rubber bands. If this has stayed in my closet for 10 years, is this any good as a rubber band? No. I've stretched this, it's just going to snap, which means on year 3 or 4, is it the same as it was on year 1? No. Rubber bands change. Why do we care? Well, if I apply a certain amount of force, would I expect the rubber band to stretch a certain amount? Sure. If I double that force, would I expect a rubber band to double in stretch? Well, year 3, year 4 is going to be doing the same thing. Rubber bands are a bunch of organic molecules that just pull past each other, and the longer you stretch it out, suddenly the harder they're pulling back. We can't use these for measurement. They fail on us. They change on us. So what could we use that as you stretch it, you could use it to measure? Well, how about something like this? This is a scale. What kind of a scale is it? What do you see in here? It's a spring scale. I got these about 10 years ago. Have they changed over time? No. As long as the spring isn't rusting or failing that way, this spring pulls back exactly as hard as it did when I first got it. But more than that, springs have a beautiful tendency to be constant. If I pull it twice as hard, it stretches twice as much. That's why if you look at the scale on this, the scale is a linear scale. As the spring stretches, if it stretches twice as much, it's registering twice the force. 3 times as much, 3 times the force. So springs are incredibly useful. Plus, because they are long-term devices, we can use them in all sorts of things to make sure the thing is restored to balance. You have springs in your car. When you fall into a pothole and it compresses your wheel down, rather than suddenly hit the car with a tremendous amount of force, which might start cracking things, the spring absorbs all of that excess force on the car and slowly restores the car to its proper position. Springs restore. That's the important part. I have 2 little springs here. This one, if you will see, is what a spring is supposed to be. This one didn't restore properly. Why not? Well, a lot of you can relate to this tale. Remember that Christmas morning where you got a Slinky? And you were the only one who got a Slinky? And your brothers or sisters grabbed one end and you pulled the other end and pulled the other end. And all of a sudden you didn't care if they got the Slinky anymore because it wasn't a Slinky. It was a weirdly coiled wire. If the Slinky doesn't go back to being a nice tight spring, you've broken it. This spring no longer is functioning as a spring. For example, in class, in earth science especially, we use these springs to demonstrate things like S&P waves and earthquakes. In physics class, we use it to start demonstrating how waves really work, and you start seeing things you thought you've seen, how these things would work, how like a jump rope works when you're twisting it back and forth. You'll see things you didn't really quite understand what you were seeing before. But is this spring healthy? Sure, look at those coils, nice and tight. What happened to this spring? Look at that. It didn't restore. Somebody pulled this too far. Could have been me. But it just got pulled too far, so it no longer is functioning as a good spring. But man, it sure is making a mess on my desk. Anyway, let's talk about the spring constant and some of the mathematics that we use for it. Very, very simple mathematics, but it kind of puts it together. One of the things springs do is they store energy. So we can use them to talk about energy storage as well. And again, we're moving on to electricity after this. So energy is important, and stored energy certainly. So the first equation with springs, check this out. Pretty cool equation. The force on a spring, F sub S, equals K. Well, K, that stands for the spring constant. We'll talk about that. K X. X is just how much the spring stretched from its equilibrium position. Okay, so this is going to be measured in meters. This is going to be measured in newtons. Let's solve for K and see what we got. K equals, well, if I take this divided by X, right? So K equals the force on the spring divided by the stretch on the spring. The units would be newtons per meter, not Newton times meter. That would be work. This is newtons per meter. In other words, how many newtons would it take to stretch that thing 1 meter? Now we understand there's a lot of springs that you're not going to stretch 1 meter and have it remain a spring, but everything normalizes for that. So if it took 1 Newton to stretch it 1 centimeter, that's 100th of a meter, it would take 100 newtons to stretch it a meter, right? So if you had a spring long enough, it would do that just fine. But those are the units we use. We never cancel these into anything, by the way, because it makes sense to talk about a Newton per meter. So that's the formula, a remarkably simple formula to use, but you end up with a spring constant. So each spring has a spring constant. If you have a very wimpy spring, for example, in this scale only goes up to 1 kilogram maximum. That's the most it'll measure. This scale will measure up to 5 kilograms. So the spring has a spring constant 5 times greater than the other spring. So each spring has a particular spring constant. And that shows how it will react to something being put on it. Look at this spring. This is a huge spring. We could hang, if this was hanging from the ceiling, I could hang my whole weight off it and it would hardly stretch at all. Other springs, if I hung my whole weight off it, they would turn to wire right away. So each spring reacts differently. I have a little setup here. Why don't you check this thing out here? All right. These are 5 springs with different masses hanging on them. So this doesn't go down quite as far as this. This goes further, this goes further, and so on. So those are all different spring constants on those springs. Pretty cool. All right. The one other formula worth talking about, I'm not going to show you how to solve these problems. This is the easiest physics we've had in a while. So there is one other formula that is worth talking about. It's also on your reference table. And that's talking about how much potential energy is stored in a spring. Well, how much potential energy? That equals 1/2 the spring constant times the distance, squared. So if I stretch a spring twice as much, how much more energy is stored in it? PE is then proportional to the square of the displacement from equilibrium position. So that could be immediately a lot of energy stored in it. If you pull a spring twice as hard or twice as far, you displace it twice as far, there's 4 times more energy stored in it than the earlier displacement. So if we were to graph these, force versus stretch, for a spring, it would be nice just like that. Very straightforward. Force and stretch is going to be just like that. If I were to graph the potential energy versus the stretch, what's that graph going to look like? All right. Well, if I mark here, this would be my first point. But if I've stretched it twice as far, it's going to go up here. So what we're going to see is a graph more like that. as you stretch it, you're storing much, much more potential energy in it because it's proportional to the square of the potential energy. So that's the idea of springs, and I think that's pretty good. All right? Have yourselves a great day. Thank you very much for putting up with all this. And now you know a little bit about springs. Think about where we use these. A lot of the scales that we use are in stores. If you're measuring out vegetables, that's a spring scale. And you'd see it's certified by the government to make sure it's reading properly. Spring scales can last for ages and still give you the absolutely correct readings. If you step on a scale to weigh yourself in the morning, that's a spring that you're stretching out, almost certainly on that scale. And they just calibrate it to see how far you stretched the spring. If you stretch it twice as far, you weigh twice as much, right? Just like that. So we use springs all over the place, but we have to use the right springs in any application. If the spring is too tight, you can't really move the object. If the spring is too loose, it doesn't restore it. So we need a very specific spring constant that people can use to talk back and forth about what the value of a particular spring is. Have a great day. Bye-bye.